Pushing a cargo ship just 2 knots faster burns 35% more fuel. Not because the engines are weak, because the power needed to move through water rises with the cube of your speed. Double the speed, 8 times the power. This is the engineering reason the largest vessels on Earth are actually designed to go slower. And the physics behind it is far more brutal than you'd expect. The idea that a cargo ship could just be given a bigger engine and sent racing across the ocean runs headlong into a harsh law of physics. Every knot added to a ship's speed brings a far steeper price than most expect. Naval architect Henrik Berg once put it plainly: the myth that speed equals profit ignores the cubic power law. A modest speed bump can double fuel use. At the heart of this problem are two kinds of drag. Frictional resistance comes from the hull sliding through water, scraping against billions of molecules along its surface. This friction rises almost linearly as speed increases, but that's only about 30% of the story. The real giant is wave-making resistance, which explodes as the ship pushes faster and faster. At typical cruising speeds, wave drag swallows up about 70% of the total resistance. As the ship nears a Freud number of 0.3, about 22 knots for a 400-meter vessel, the bow and stern waves start to reinforce each other. The result is a spike in resistance so sharp it can only be captured by high-precision CFD simulations, which now match real-world total tank tests within a percent. This is why the power needed to move a ship doesn't just rise with a speed, it leaps. On the KRI, as O container ship, a 1-knot increase from 22 to 23 knots means the engines must deliver 12% more shaft power. 2 knots more, nearly 40% extra. The relationship isn't just cubic. As wave-making takes over, the exponent creeps even higher. This is why a small gain in speed demands a mountain of extra fuel, and why the question of why not faster always turns into a battle with the physics of water itself. Hull design is a negotiation with the laws of geometry and the realities of global trade. The length-to-beam ratio, or LB, sits at the heart of this compromise. For the world's largest container ships, LB typically lands between 6.5 and 6.8. A longer, slimmer hull would glide through water with less wave resistance, but that approach quickly hits a wall. The ship's beam, the width at its widest point, cannot be stretched or squeezed at will. It is dictated by the standard 8-foot container stacked side by side across the deck. For a 24,000 TEU vessel, this means a beam of about 58.6 meters, matching the reach of modern port cranes. Widening the ship for more stability or narrowing it for less drag would force a redesign of every major terminal, a cost no shipping line can accept. Even within these boundaries, small design tweaks carry consequences. The bulbous bow, for example, is engineered to carve a trough in the water that cancels out part of the bow wave. But this trick only works in a narrow speed window, about 8% resistance reduction, centered at 22 knots for most ultra-large ships. Drift even 2 knots off that target, and the bulb can backfire, adding drag instead of saving fuel. The margin for error is razor thin. Material choice adds another constraint. High-strength steel, like NV36, is favored for its balance of strength and weldability. But lighter materials, such as aluminum or composites, cannot deliver the necessary stiffness for 400-meter hulls without becoming prohibitively thick and heavy. Every extra meter of length or reduction in beam means more stress on the structure, demanding thicker plates and heavier reinforcement, which eats into cargo capacity and efficiency. These geometric trade-offs mean that the shape of a cargo ship is locked in by a blend of hydrodynamic theory, port infrastructure, and the physics of steel. The hull cannot simply be stretched or squeezed to chase higher speeds without sacrificing the very efficiency and capacity that make global shipping work. Even if a ship's hull could somehow be made perfectly efficient, another wall stands in the way: the machinery itself. Pushing a container vessel beyond its typical cruising speed isn't just a matter of ordering a bigger engine. The relationship between power and speed is steep, but the real trouble begins with the propeller. At around 80 meters per second, the tips of a ship's propeller blades begin to cross into dangerous territory. This is the threshold where cavitation, tiny vapor bubbles forming and collapsing with explosive force, starts to eat away at the metal. Once cavitation sets in, each revolution chips away at the blade, reducing efficiency and risking catastrophic failure. The MSC Daniela, a 13,000 TEU vessel, experienced severe propeller erosion after running at a sustained 22 knots in cold Atlantic waters. Post-incident analysis tied the damage directly to cavitation at high tip speeds, confirming what engineers have long warned: there's a hard ceiling set by physics, not by ambition. The next barrier is engine power density. The biggest marine diesels today deliver about half a megawatt per ton. To push a ship even a few knots faster, designers would need to add massive engines, each weighing hundreds of tons and eating into space meant for cargo. More power means more weight, more volume, and more heat to manage. Lars Jensen, a chief engineer at Maersk, summed it up: "We reduced cruising speed by 2 knots fleet-wide, saving 30% of fuel while only adding a day to most routes. Chasing higher speeds would reverse those savings instantly." The mechanical limits of propeller design and engine density are not just footnotes. They are the hard stops that keep cargo ships from simply dialing up the throttle. Fuel is the single biggest line item on a shipping company's balance sheet, and its price can make or break a route overnight. In 2008, bunker fuel prices surged to $850 per ton. For a ship burning 200 tons a day, that is $170,000 just to cross the ocean every day. When Maersk's board studied these numbers during the fuel crisis, they saw a simple equation: slow down, save billions. By reducing cruising speed by 4 knots across the fleet, Maersk cut annual fuel costs by $2 billion, even though each voyage took a couple of days longer. That decision, known as slow steaming, became the new normal almost overnight. But fuel price isn't the only lever. The International Maritime Organization tightened the global sulfur cap from 3.5% to 0.5% in 2020 and will drop it even further to 0.1% in emission control areas. This policy forces ships to burn cleaner, more expensive fuel. The cost of compliance can double overnight, especially for vessels operating at higher speeds, where fuel consumption and emissions rise cubically with every extra knot. Even the lure of a charter premium for faster delivery, often less than 50 cents per container per day, can't offset the millions spent on extra fuel. An IMO economist put it bluntly: the $2 billion Maersk saved by slowing down dwarfed any minor penalties for late arrivals. Today, the same calculus underpins global decarbonization efforts. Fast ships mean high costs and high emissions, and both regulators and company boards now treat speed as a risk, not a selling point. Steam-powered freighters in the 1850s lumbered across the Atlantic at barely 8 knots, held back by low-pressure boilers and primitive hull shapes. By the 1930s, the arrival of diesel engines pushed average service speeds to 12, sometimes 15 knots, a leap that shrank ocean crossings by days and redrew trade maps. The post-war era brought cellular containerization, and with it, a new appetite for speed. Shipyards stretched hulls, refined bows, and squeezed every extra knot from new engine designs. By the early 2000s, mega container ships carrying over 10,000 TEU routinely sailed at 22 knots, burning through fuel to keep global supply chains humming. But in 2009, a new reality set in. As fuel prices spiked and emissions rules tightened, the industry pivoted almost overnight to slow steaming. Operators cut speeds to 16 or 18 knots. The pace that once defined progress became a liability, and the relentless race for speed gave way to a search for efficiency. The story of shipping's speed curve is one of ambition checked by physics, and of each generation learning, sometimes painfully, where the real limits lie. Dr. Maya Patel's latest CFD runs capture the tipping point that defines the modern cargo ship's speed envelope. Her simulations trace the moment a 400-meter hull pushes past a Freud number of 0.3. At that threshold, the wave system around the ship stops behaving linearly. Bow and stern waves begin to synchronize, and resistance surges far beyond what the cubic law alone predicts. Patel's data show that, for an ultra-large container ship, this resonance sets in at just over 22 knots. Beyond that, no amount of extra power can flatten the spike. Wave-making resistance dominates, and efficiency collapses. Naval architect Henrik Berg distills the lesson from decades of design. We can nudge the envelope by slenderizing the hull, but that means losing rows of containers. Every tweak to chase speed comes at a cost to capacity or stability. Today's ultra-large ships are built for 16 to 18 knots, not because shipyards lack ambition, but because the numbers are unforgiving. The optimal balance, where fuel, cargo, and structure all align, sits squarely in the narrow band that modern CFD and real-world data now confirm. The speed envelope is not a guess. It's a boundary set by the physics of water and the realities of global trade. Global trade depends on ships that move not at breakneck speed, but at the edge of efficiency. Today, every knot faster means exponential fuel costs and emissions. As demand for shipping grows, the real challenge isn't speed, it's building a future where efficiency drives progress. Thanks for watching.